Hello. In this first lecture, we will try to motivate the need to study Lebesgue's theory of measure and integration. So we are going to motivation. So from the time of the Greeks, the problem of computing the area enclosed by a curve has been at the base exercising the minds of scientific thinkers. This crucial question, which is at the root of integral calculus, was treated as early as the 3rd century BC by Archimedes. He computed the area of the circle, the segment of a parabola, and other such figures. What he did was to use the method of exhaustion, which means to exhaust the area by a sequence of polygonal domains, compute the area of the polygonal domains, and somehow compute the area of the required figure by means of some kind of limiting argument. And during the 17th century, many such areas were calculated, and in each of these problems was solved by some ingenious device and suited for the special case. So one of the main achievements of calculus was to give a powerful and general method to replace these special techniques. So from the time of Archimedes until the time of Gauss, the attitude was that area is something which is intuitively known. We know what it is. We don't have to define it. We just need to compute it. But before Cauchy, there was no formal definition of the integral in the precise sense of the term. One was often limited to saying which areas one had to add, which areas one had to subtract, so as to get the area, which is, of course, we know, an integral. Cauchy, with his concern for rigor, and this is characteristic of modern mathematics, defined the continuous functions and their integral in much the way as we do now. So to arrive at the integral of a continuous function f, defined on an integral ab, so f from ab to r is continuous. So we want to know what do you mean by integral a to b f of t dt. So he computed sums of the form s is equal to sigma over I f of ti xi plus 1 minus xi, where a is less than or equal to x naught, a equal to x naught, less than x1, etc., less than xi, less than xi plus 1, etc., less than xn equal to b. So this is called a partition. Okay, and you have that ti is a point belonging to the interval xi plus 1. And then, using a suitable passage to the limit, he defined the integral. Now, for a long time, some discontinuous functions were also evaluated by, their integrals were evaluated by showing that Cauchy's method still applied. And it was Riemann who systematically investigated the exact scope of Cauchy's definition. So in what follows, we will recall briefly the Riemann integral and also examine what are its drawbacks, so that we will motivate thereby the need for the new theory of integration, which will be Lebesgue's theory. So you take AB, so Riemann integral. So AB in R is a fixed interval, and f from AB to R is a bounded function. So that means m less than or equal to fx less than or equal to some capital M for all x in AB. Okay, so then we look at a partition. So P is of the form a equal to x naught less than x1, etc., less than xi plus 1, and so on, less than xn equal to b. Okay, the n can change, the points are going to change, so we are going to take different kinds of partitions. And then we define mi to be the inf of f of t belonging to xi plus 1, or rather the xi minus 1 xi, and then capital Mi to be equal to the sup of f of t on t belonging to xi minus 1 xi. Because we are starting with x0, I am doing it this way. Then we define what are called the upper and lower Darboux sums. So we have upper and lower Darboux sums. So the lower Darboux sum, depending on the partition and the function, is equal to sigma I equals 1 to capital N of xi mi, the lower value, xi minus 1, and the upper Darboux sum is sigma I equals 1 to N capital Mi xi minus 1. Okay, and then we define the lower and upper integrals. So integral a to b with a lower sign ft dt is equal to the sup of LPF taken over all possible partitions, and then we have the upper integral a to b of ft dt is equal to the inf of UPF taken over all possible partitions. Now the function is Riemann integrable if the two are equal. So a upper b f t dt is equal to lower integral a to b f t dt, and the common value is called the Riemann integral, and this is called integral a to b f t dt. So this is how we define the Riemann integral. Now f is bounded, so we have that m times b minus a is always less than equal to LPF, which is less than equal to UPF, which is less than equal to capital M b minus a. In fact, this L less than U is true for any two different partitions also. If I have P1 and P2, two different partitions, L P1F will be less than equal to U P1F, one can see. So therefore, the sup and the inf are always existing because you have that these sums are all bounded, and therefore the lower and upper Darboux integrals always exist. Whether they are equal or not is a delicate question, so we have to investigate. So the being Riemann integrable means that these two are to be equal. Now if you have a partition P, so we define the mesh size of the partition to be the maximum of the lengths of the subintervals 1 less than equal to I less than equal to n of xi minus xi minus 1. So you take the largest possible thing, and now if you take Ti to be a point belonging to xi minus 1 xi, then we define the following sum. SPF is equal to sigma, like Cauchy did, 1 to n f of Ti xi minus xi minus 1. So caution here, namely this is notation is not a very good notation, because the SPF, it looks as though it depends only on P and F, but it also depends on the choice of the points T. So if you change the points T, the sum is going to change. But if I am going to bring that in, we are going to have very cumbersome notation. Anyway, we won't use much of this, and therefore we will leave it at that. So this, please remember that this is a thing which also depends on the points Ti. So now we say, so definition, you say that limit of mu p tending to 0 of SPF equal to A. So what does it mean? So this means for every epsilon positive, there exists a delta positive such that for all partitions P such that mu P is less than delta, and for all choices of Ti, I equals 1 to n, SPF minus A is less than epsilon. So this is very important. So how you have to change. So this is a very strong condition and you have to do this. So now, so the first theorem in Riemann integration. So for all these results, you can look at Rudin's real and complex analysis. I mean principles of mathematical analysis. This is a standard book which you can very easy to get, and therefore you can see this in the in Rudin's book, and so you must have done it in your real analysis course. So F is Riemann integrable if and only if limit mu p tending to 0 SPF exists, and you have, and in fact integral a to b ft dt equals limit mu p tending to 0 SPF. So this is a very important theorem. Now the next important theorem of which I want to recall from Riemann integration is if f is continuous, or f has at most a countable number of discontinuities. We will improve on this later in this course, but anyway, for the moment, f is continuous or has at most countable number of discontinuities, then f is Riemann integrable. So let us look at an example. So you take 0, 1 and you take a numbering of the rationals. So its rationals are countable, so you can write them in some order. Okay, it doesn't matter how you are going to write it. So you define fn of x to be 1 if x is equal to r1, r2, rn, and 0 otherwise. So this function f is discontinuous. F is discontinuous only at r1 to rn. So it has only finite number of discontinuities. So by the previous theorem, Fn is Riemann integrable. But in fact, you can apply the definition straight away, the partition definition which we have seen just now, compute the lower sum, compute the upper sum, and you can easily prove that in fact integral 0 to 1 Fn t dt is equal to 0. So this you can check. So check using the definition which we have just given. It's a simple exercise which you probably already done in your course. Now let us now consider f of x equals limit n tending to infinity fn of x. What is this equal to? It's equal to 1 if x is rational and 0 if x is irrational. Because slowly as n increases to infinity, you are going to cover all the rationals, and therefore you will have. Now if you take any partition, they are going to, each subinterval will have both a rational number and an irrational number, because both sets are dense, and therefore small mi is always 0, capital Mi is always 1. So this implies for every partition P, you have LPF will be just 0 and UPF will be equal to 1, since Mi equal to 0, capital Mi equal to 1 for all n. Okay, whatever may be the point, this thing. And therefore you have that the lower integral 0 1 ft dt equal to 0 and the upper integral 0 to 1 ft dt is equal to 1, and consequently f is not Riemann integral. So we have already come to our first drawback, namely a sequence of Riemann integrable functions need not be Riemann integrable. Okay, now things become worse. So Fn Riemann integrable does not imply f is Riemann integral. Okay, in general, so taking pointwise limits, you cannot assume that, but assume that f is Riemann integrable. Even then, things cannot be very good. So let us take another example. So let us take fn of x equals n square x into 1 minus x square power n. Okay, then for every x in 0 1, we have fn of x goes to 0 as n tends to infinity. Prove. This is simple exercise to show that the limit of these functions is 0. Okay, so then, but you now take integral 0 to 1 x into 1 minus x square power n dx. So this is straightforward calculation. You can calculate it and it will be equal to 1 over 2n plus 2. So n square times this function is a given function. So integral 0 to 1 fn x dx is equal to n square by 2n plus 2, which tends to infinity. But integral f of x dx 0 to 1 is 0 because fn goes to f, which is identically 0. And therefore, the limit of the integrals, even though the limit function is Riemann integrable, the limit of the integrals is not equal to the integral of the limit. Thus, limit n tending to infinity, integral fn t dt 0 to 1 is not equal to integral 0 to 1 ft dt, which is, if I want to write this is equal to limit fn dt. Okay, so you cannot take the limit inside the integration sign. Okay, so this is a major thing. Now, even if so here of course it went to infinity, but let us take for instance that if you take fn of x equal to nx times 1 minus x square power n, then integral fn t dt will converge to 1/2. Okay, and that's again still not equal to 0. Here it went to infinity, here it goes to a finite number, and still of course we do not have this condition here that the limit of the integrals is not equal to the integral of the limit. So we have that the limiting process, integration is itself a limiting process, and then we are taking a pointwise limit of functions, and we have just seen that these two do not commute. So we have two problems. One is the limit of a pointwise limit may not be Riemann integrable even though every member of the sequence is Riemann integrable, and secondly, even if it is Riemann integrable, we cannot assert that the limit of the integrals is equal to the integral of the limit. Okay, so now is there any hope? I mean, is there any condition for which you have this? So if fn goes to f uniformly, that means you have that given any epsilon, there exists a capital N such that mod fnx minus fx is less than epsilon for all n greater or equal to n and for all x in 0, 1. Okay, so then you suppose you have this is again a very strong condition, then of course you have a theorem that fn goes to f uniformly, then integral, and Fn is Fn Riemann integrable for all n, implies F is Riemann integrable, and integral Fn dt 0 to 1 goes to integral 0 to 1 f of d. Okay, so this is of course a very costly condition, and therefore it is so we find that for the theory of integration, we need a theory of integration which is more friendly towards taking limits. After all, in analysis, taking limits is our bread and butter, and we have several limiting processes. We would like limiting processes to commute so that computation will be easier, and for many other reasons also, and therefore we would like to know if there is a better integration theory than this one, such that more functions become integrable. Like, so that this example, for instance, this in the example which we saw, the rational f, where f is 1 is if it's rational, 0 for x irrational. Now that sequence is obviously not uniformly convergent, because if it were uniformly convergent, then the integrals f would be Riemann integrable, which it is not. And therefore, in fact, this validity of this theorem, if this becomes equal or not, that is itself a test, whether one of the tests for uniform convergence of a sequence of functions. We say Fn goes to f, and if you want to say does it converge uniformly, and then you check if this condition holds. If it doesn't hold, that means the convergence has not been uniform because of this theorem which we just stated. Okay, so we want to know if you have a theory of integration where more functions become integrable, not just for the fun of generalization, because we would like, under reasonable hypotheses, that limits of integrable functions are integrable, and also the integral of the limit is equal to the limit of the integrals. So these are the properties which we would like to know. Okay, now the way the Riemann integral is defined, a certain amount of continuity is forced into the theorem, because we have this following theorem here. F is Riemann integrable if and only if limit SPF exists and this is equal to the same. So we want that for the function to be Riemann integrable, SPF exists. Now what is SPF? SPF is nothing but the for all choices of points. So if you take mu p going to 0, so for small intervals, Ti, if you change a bit inside the subinterval, SPF should not change too much, because otherwise then the limit will not exist. This is what is happening in case of the function which is 1 if rational, 0 if irrational. If you change a point from rational to irrational, SPF will collapse. Okay, so that is why that function was failing to be Riemann integrable. So we have that small close by values should still be close by. This is but that is what continuity is, right? So some amount of continuity is enforced. Of course, we can excuse a small number of discontinuities, as was mentioned in that theorem, and that is a theorem which says how much we can excuse. Okay, so the function may be discontinuous, but right now in the Riemann theory, if it has a countable number of discontinuities, then of course we can excuse it and still do something. If the function will be Riemann integrable. So the function is more or less continuous as far as the Riemann to be Riemann integrable. Okay, and the number of discontinuities is severely limited. Now, the idea of Riemann integration is definition of the integral. What we do, we take a partition and then we take the points in the partition. So we are following the function along the x-axis, along the abscissa. So we are taking the function as we proceed along the x-axis, and therefore we are forced to compare nearby values. Now, the differentiation is a local phenomenon. If you want to differentiate a function, then of course we have to look at the values nearby to find the rate of change of the function. But integration is something global. You don't have to, we are not worried what happens nearby values, what really we are worried about is the global behavior of the function. Let us take the example of floods. Suppose you have floods somewhere, as it happened in Chennai recently. Now, if you are the corporation councillor, you would be walking along your ward and seeing how the situation is, because that's all you are interested in. But the chief minister or the prime minister will not do that. The chief minister or prime minister needs to have a global picture of the disaster, so he will fly. So he will have an aerial survey of the entire damage. Now that is the idea of Lebesgue. Now Riemann said, I will walk along the x-axis, therefore, and look at the function, take it as it comes. But Lebesgue said, no, let us fly on the y-axis and take a global view of the function. So we take a particular value on the y-axis. So we don't work on the domain, we work on the range. We take a value on the y-axis and then look at the entire set which takes this particular value and study it and use it to define the integral. So let us give an example. So let us take P to be a partition of AB, and you take f of x to be the following function: sigma I equals 1 to n alpha I chi of ei. Okay, so where ei is the interval xi minus 1 xi. So what is chi of a? If a is any subs, a is contained in AB, chi of a of x, this is a characteristic function. This is equal to 1 if x belongs to a and 0 if x does not belong to a. So this is called the characteristic function. It's also called the indicator function. Another name for it is indicator function of the set A. So we take this, and so such a function is called a step function, because you take various intervals. So you have alpha 1 here, alpha 2 here, alpha 3 here, alpha 4 is this, and so on. So this is called a step function in this case. Okay, so now this function, of course, only has a finite number of discontinuities, so it is Riemann integrable, and you can check. So you can check that integral of f of x f of t dt from a to b is nothing but sigma of alpha I xi minus xi minus 1. Okay, I equals 1 to a. One can check this. This is standard. Just apply the definition and we will get it. Okay, so it's a good exercise to do these things because now by Lebesgue's method, what we are going to do is we will look at E alpha. For every alpha in R, we take E alpha is set of all x. So set fx equals alpha. We take this set. So we have that E alpha equal to 0 if empty set if alpha is not equal to alpha I for all I, and then E of alpha I is precisely the set EI. And then you take the length of the interval over which you have this, and you have the alpha, and you the integral is so the Lebesgue integral equals summation over all alpha. So I'll put it because alpha varies, okay, alpha times length of E alpha, and that's equal to sigma I equals 1 to n again, alpha into xi minus xi minus 1. So this is the same answer. We are not getting anything new, okay, but it's just a method. So let us assume you have a merchant who has been doing sales all day, and at the end of the day, when he closes his shop, he wants to know how much money he has earned today. So there are two ways he wants to compute the First, he can put his hand into the till, take the number coins or notes one by one and add the values. That is one way. Other is to empty the till, sort out all the coins and notes according to their denomination, see how many coins are there in each denomination, find those values and add those values. So that is the first is the method of Riemann, where he takes one by one and adds them. The other is taking the various denominations, seeing how many notes or coins are there in each denomination, and then adding those values. So that is the method of Lebesgue. So if you both will give, if you are careful, both should give you the correct answer. But the second one is definitely more efficient, especially if it involves a lot of money. If you have gone to some huge temples like Tirumala, for instance, you would have seen how they sieve all the thing and separate the contributions according to denominations and count them. Okay, so this practical example of this method. Okay, so the Riemann integral, what does it do? It approximates, so Riemann integration, you approximate f by step functions. That's exactly how we have defined the integral. Now, what is Lebesgue integration? Approximate f by simple functions. That means sigma alpha I chi of ai arbitrary sets. Again, it can't be always arbitrary. I'll put it within inverted commas. We will see these things. This is the second giant leap. So there are two leaps of imagination which we have here. First is to walk along the y-axis so that you get a global view of the function, and the second is to replace the step functions, namely which depends on partitions and intervals, by writing this. Now you compute, so integral of phi t dt for Lebesgue is by definition sigma alpha I length of ai. Now here is the catch. What do we mean by length of ai when ai is not an interval? So we said, see this, I got a very big generalization by looking at simple functions, but I do not know what is meant by length of ai. So that is where we come to the theory of measure. So we have to generalize the notion of the length of interval, area of a square or rectangle, volume of a rectangular parallelepiped in 2 and 3 dimensions respectively, to length, area, volume of arbitrary sets. Well, we can't do it for all sets, we will see it, but then this is the notion of a measure. So this notion, generalized notion of length or area or volume, or in general, you can do it on any arbitrary set, and that is what we are going to do, and that is the abstract theory of measure, from which we will develop the theory of integration. So next time we will look at that. Thank you.